Up until this point, we've been focusing more on the feedback aspect of our feedback instability. So let's switch our attention to looking now at the stability of our feedback circuits. So let's start by considering the ideal closed loop gain of just a general system. So our ideal closed loop gain after we've incorporated feedback is given by A sub f, so gain with feedback, and in general that's our output signal divided by our input signal. So again, I'm keeping it very general. These could be voltages or currents. And we said that this is equal to A divided by 1 plus beta A. And so remember, A here is our open loop gain. Beta was our feedback transfer function. And we had also defined this term called our loop gain, which we said was equal to T, and T was given as beta times A. So we could come back and we could rewrite this then as A divided by 1 plus our loop gain T. So now if we think about this open loop gain, this quantity A, we know that our A is actually going to be some function of individual transistor parameters. So let's just say it's a function of our transistor parameters. And so unfortunately, we didn't have enough time to look at this in this class, but if you go back and you look in chapter 7 of Niemann, what you'll see is that our transistors, like many other components, are going to have a frequency response. And so what that means is basically for our transistors, these parameters are changing as our frequency changes. Let's actually be more general and let's just say our behavior changes as our frequency changes. So what that means then is that this A, this open loop gain, is a function of frequency. So remember, in general, to make things a little easier, we can use the variable S, which is equal to j omega. So omega, of course, being our frequency information, where we have omega equals 2 pi times f. So using this, we can express A as a function of frequency just by saying A is a function of S. So now because our T, our loop gain, is also dependent on this A, it is also going to be a function of frequency. So we could rewrite our closed loop gain. So we notice that now it's going to be a function of frequency, and it's equal to our A of S divided by 1 plus T of S. So what we can see from this is that our loop gain is a function of frequency. So our loop gain is a function of frequency, and so that means as we're changing the frequency, the behavior of that loop gain is going to change. So for some more details on how to sort of determine our loop gain from an actual circuit, you can look on pages 901 to 907 in Niemann, and that goes into some good details. Again, unfortunately, it's just something we don't have enough time to cover. But what we'll see here explicitly in equations in a little bit is for certain frequencies. So if we're looking at this loop gain, so let's say for some frequencies, our loop gain becomes a value such that our negative feedback, so remember our negative feedback was basically we were subtracting when we're feeding back the output portion to our input, becomes a positive number such that we have positive feedback. So we have positive number being added back to our input. So we have positive feedback, which can lead to our system being unstable. And so what we're going to do is we want to investigate more closely this loop gain function. And if we get a better idea of the frequency response of this loop gain, T of S, then we can better understand how our circuit is going to behave with frequency and when it's stable and when it's not stable. So let's take a little closer look at that right now. And then in some later videos, we're going to look at specific systems and figure out what their loop gains are. So let's focus on this t of s. Well, we can write that as t of j omega if we want to explicitly see that frequency. And of course, when we have this j, we know this is going to be a complex value. So this is going to have some magnitude component, which is the magnitude of t of j omega, as well as some phase component. So let's start by considering, what if we have a magnitude of 1? So our magnitude of our loop gain is equal to 1, and our phase is equal to 180 degrees. Well, if we think about what that looks like on our complex plane, so we have our imaginary and our real axes like this. So our magnitude is the distance from the origin. So in this case, we would be coming over here let's do both at once. So we have 1 is our distance from the origin, and then theta is going to be our angle from this real axis, or phi rather. So we have a distance of 1 at an angle of phi. So we can see essentially this is -1. So if we come back up here to our equation for our closed loop gain, we see that for this case, we're going to have a closed loop gain that becomes infinite. And so what that means is our circuit is going to be unstable and we're going to have oscillation. And so oscillation is a topic that we're going to look at in a later unit. But for what we're talking about now, we're saying that this oscillation is not intended, so our circuit has just become unstable. So what we're going to show in some of the later videos is that if our magnitude of this loop gain is less than 1, when our phase is equal to 180 degrees, our system is going to be stable. If, however, the magnitude of our loop gain is greater than or even equal to 1 at a phase of 180 degrees, then our system is going to be unstable. And so again, we see that all of this information is going to be contained from the loop gain of the circuit. So in subsequent videos, we're going to look closer at loop gain equations for various types of circuits, and we're going to see how we can determine stability from that, and a little later on, we're going to see how we can quantify the degree of stability of a circuit using our loop gain information.